All right, welcome to the first lesson of Unit 2. Unit 2 is sort of the beginning of the rest of the semester, in that here we're going to define what the derivative of a function is and understand the derivative in relation to some things that we've already worked with: instantaneous rate of change and average rate of change. And the derivative is a tool that we're going to use over and over and over again for the rest of the year. It is one of the most important tools in mathematics as far as understanding real-world situations. And so we want to make sure that you have a good conceptual intuition of what the derivative is and why it works. So make sure that you take your time here. Don't just try and memorize definitions and whatnot. Really focus on understanding them, and particularly looking at the graphical representation so that you can kind of always have a picture in your head of what you're doing. All right, so to sort of discover what we are going to talk about today, let's look at an example. So a pretty simple situation here. The function f measures the amount of water in gallons that are in a swimming pool as it is being filled over t minutes. There's your function. Sketch a graph of f on the interval from 0 to 10, and for each part a and b, label where the values you find appear on the graph. So don't spend all day graphing this function. You could type it in your calculator or go to Wolfram Alpha or just sketch a couple of points. You know what type of function it is. The shape should be pretty basic. Then get into the questions. So go ahead and copy questions down, go through them yourself, and we'll talk briefly about what you discovered and what you found in a little bit. Okay, so hopefully that went pretty well, if not a little time consuming. But maybe you figured out a shortcut before going through all of Part B. We'll get to that in a second. So finding the average rate of change on the interval from 2 to 5, very basic again. We've done this a million times. This is simply 8 gallons per minute on average between 2 minutes and 5 minutes. So it's important to have the understanding of the real life relationship, because that's something that we're going to come back to over and over again when we're solving real life problems. So here's the change, the numerator is the change in the number of gallons in the swimming pool between 2 and 5, and we divide that by the number of minutes that it took to get on average 8 gallons per minute being put in the pool. Now of course we know that that's just an average, and that at every instant we can actually find what the amount of water in the pool is changing by. In other words, if I have a sketch of this function, each of these instantaneous rates of change would be the slope of the function at these t values. So remember that the instantaneous rate of change at a point, you can use the limit definition of instantaneous rate of change to find that value. So let's just consider how we would do this for t equals 0. So let's say we want to find the instantaneous rate of change, or the slope, when t equals 0. And the way that we can find that is by taking the limit as h approaches 0 of f of 0 plus h minus f of 0 over h. And this isn't that interesting, right? 0 plus h is just h, right? So this is just going to be f of h minus f of 0. And if I plug 0 into my function, I just get 0. So I end up with just f of h in my numerator. And so when I take the limit of this, I'm going to be taking the limit as h approaches 0 of h squared plus h over h. And I could plug h in, but I'd get 0 over 0. Luckily, I can quickly factor this and cancel an h from my numerator. And so when I do that, I will end up taking the limit as h approaches 0 of h plus 1. And plugging in now a value of 0 for h, I get that the instantaneous rate of change when t is 0 is simply 1. Or in this case, 1 gallon per minute. Okay, great. That was a lot of fun. Hopefully we understood it, right? But we want to know the instantaneous rate of change for a bunch of different t values. Well, I can go through this process when t equals 1, when t equals 2, when t equals 3, so on and so forth, and hopefully you gridded through it if you didn't see a shortcut. But what you hopefully noticed is that you spent a ton of time and you did a lot of the same things over and over and over again. And whenever we're working mathematically, we want to try and look for any repeated reasoning that we're doing and see if we can come together and bring out a general rule from that so that we're not doing all this work over and over and over again. And so in part C, hopefully you sympathize with the student who took 30 minutes to calculate the instantaneous rate of change at each of these times separately. And you thought about what could we do so that we didn't have to actually take the instantaneous rate of change using the limit definition over and over and over again. And when you thought about that, hopefully you realized, well, there's this repeated reasoning that I'm using, right? I'm continually taking the same limit. The only thing that's changing is the t value. What if we just knew what the instantaneous rate of change was going to be in terms of t, and then we just plugged t in when we wanted to figure out the particular instantaneous rate of change? And we did a couple of examples like this towards the end of the last unit, where instead of plugging in a specific point, we actually found the instantaneous rate of change for any point. And this is what's called the derivative. And so we can actually take the instantaneous rate of change for any time t. So this is what it would look like. Instead of finding the slope when t equals a, we're just going to find the slope for any value t. And at first this might seem a little confusing, but instead of plugging in a specific value, we're just going to leave it as t. So take the limit as h approaches 0 of f of t plus h minus f of t over h. And this looks a little daunting, right? Because notice that I don't have any numbers in here, right? How is this ever going to work out? Well, first, pause the video, work it out, see what you get, and you'll notice that you end up with an expression in terms of t. Think about, is that something that might be helpful, and why? So hopefully you went through with this, and when you get an expression in terms of t, hopefully you're able to realize how advantageous this is. Now you can calculate the instantaneous rate of change for any value t. And you can check your work in part B, plug in values like 1, 2, 3, 4, 10, and see if you get the same thing, and I think you'll notice that you do. Let's go ahead and take a look at what this solution would be. So I went through this rather quickly, but essentially what I did is instead of plugging in 2 plus h into my function, I just plugged in t plus h. So it would be t plus h squared plus t plus h minus, and I distributed the negative in when I calculated f of t, which is t squared plus t. Distributing the negative gives me negative t squared minus t. I FOILed and canceled like terms, and canceled out some values and then added like terms and ended up with 2th plus h. I factored out the h, which allowed me to cancel my h values, so I didn't have 0 over 0. And then all I'm left with is 2t plus 1. Well, notice I'm taking the limit as h approaches 0. 2t plus 1, I can plug h into that, no problem, because there's no h whatsoever. So I'm just going to end up with 2t plus 1. Now, if you go back and you think, well, what does this tell me? This tells me the instantaneous rate of change at any t value. In fact, let's plug in 0. 2 times 0 plus 1 is 1. Isn't that what we found originally? It is. If you plugged in 10, you'd get 2 times 10 plus 1, or 21, which would be the instantaneous rate of change at t equals 10, or at 10 minutes. And so now we can find all these values really quickly. You could find them all in your head in about a minute. And so you've cut down this 30-minute laborious task into one limit problem and then maybe a minute's worth of mental math. This is what's called the derivative. What we did here is we took the derivative of our function f of t, which told us the instantaneous rate of change for f at any value t. And as you might have guessed, this is going to be pretty powerful. It was already very powerful in helping us find the answer to part B in maybe a tenth of the time. So let's go ahead now and define what we just discovered as the derivative of a function. All right, so here is the definition of the derivative of a function. So we've looked at some very important concepts so far. We've defined a limit. We've defined what it means to be a continuous function. That's incredibly important. We've defined what instantaneous rate of change is. And this is now the biggest definition that we have so far. We're going to come back to this over and over and over again over the next couple of weeks. So the derivative, and this is really just a recomposition of what we talked about in the discovery problem. The derivative of the function f with respect to the variable x, that means that the independent variable here is x, is the function denoted as f prime. This is how you say this, f prime, given by f prime, which is written in terms of x, is equal to the limit, as h approaches 0, of f, the original function, of x plus h minus f of x over h, provided that the limit exists. Obviously, if the limit doesn't exist, we can't define this function. So let's take a step back and really make sure we understand what this is saying. This is giving us a lot of power, right? Now, instead of just finding the instantaneous rate of change at any particular point, we now have a way of writing this function f prime of x, which will just allow us to plug in values of x and find the instantaneous rate of change of f for that particular value of x. So what you can think of f prime of x as, it's the derivative of f, which is another way of saying a function that gives you the slope at any point of f, or the function that gives you the instantaneous rate of change at any point of the function f. And the derivative is a very powerful tool that we will come back to over and over again. So what I'm going to do now is going to sketch a graph, and hopefully we can get a graphical representation and understanding of what f prime of x is. Okay, so hopefully we'll be able to get a visual representation kind of in our heads of a couple different ways to interpret the derivative as the function that gives you the slope of f at any point you want. So let's first consider that we have just some function f of x, and in this case it looks to be a quadratic function, but that's irrelevant. Any function that we have, and the derivative f prime of x can be applied at any x value to give you the slope of f at that exact point. So for example, if you want to know, let's say this point A here, you want to know the instantaneous rate of change at this point A. To find that, you would use the derivative f prime of A. Okay? So once you found f prime of x, you could plug in the value A, and that would give you the instantaneous rate of change of f at that point. Remember, f prime of x is in terms of x, meaning you can plug in any x value. Also meaning you can plot or graph f prime of x and see what it looks like. And we can do that kind of from scratch just by looking at our value of our function f and seeing what does the rate of change appear to be as we go through our function. Well, notice that here the rate of change, the slopes, should be negative, right? So if I'm graphing f prime of x, I should have negative values. And clearly they seem to be shallowing out because eventually they're turning positive. So we should have, so let's think about what this might look like, right? We have bigger negative values for the slope, so that means f prime would be giving us bigger negative values, smaller negative values, smaller negative values. What's the slope right here at the vertex of my quadratic? Well, it should be 0, right? The slope would be perfectly flat. So f prime at this exact point should hit 0. And then it's going positive, right? And more positive and more positive. So then f prime should be getting positive and more positive. So we can actually sketch a graph of this knowing that it's going to hit 0 right about there. We can say, okay, look, f prime of x might look something like this. Okay? And I guess let's label it f prime of x. Okay? And so the relationship between f and f prime, we're going to talk about this more and more, but I just want us to begin with a conceptual framework, is that the derivative of f is f prime of x, and that gives us the instantaneous rate of change, or the slope of the original function f for any value x. Okay? All right, so let's apply this definition to some basic functions and find our first derivatives. All right, so here is a problem for you to try. Go ahead and copy this down, go through it yourself. I will go through it quickly and then give you just one or two more to do completely on your own. Right, so finding f prime of x, I'm finding the derivative of f, and so I'm using my definition here. F prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x divided by h. And now we plug x plus h in to our function, f, rewrite our limit statement, and we'll have x plus h cubed minus x cubed over h. Okay? And at this point, you're going to have to cube this out. So just a reminder, pull this off to the side for a second. We have x plus h times x plus h times x plus h. So go through first, take it two at a time, and then what you'll have is you'll have x squared plus 2xh plus h squared. And then when you multiply by x plus h, you literally just have to distribute the x in to all of these pieces and the h in to all of these pieces and collect like terms. We'll take a look at what you get in just a second, but I want you to go through that yourself. Alright, so there I have it. Notice that this minus x cubed is still the minus x cubed that we got from taking f of x, that's just x cubed. And then everything else here is what ends up happening when I do x plus h cubed. And so notice that I have a bunch of things that are going to kind of collect themselves and make this a lot easier. So x cubed minus x cubed is 0. And so now I just have a situation where each of these terms has an h, so I need to cancel out my h in the denominator because that's what's making this undefined, and so I can factor that out, and that'll put me in really good shape. So I have now the limit as h approaches 0, and I factored out an h, so I have h times 3x squared plus 3hx plus h squared divided by h. H over h is 1 since we're taking the limit as it approaches 0, not actually computing it at 0. And now I can plug h in. This piece will go to 0, this piece will go to 0, and I'm left with 3x squared. So what we notice here is that we've found the derivative of f with respect to x, meaning a function f prime of x, which now whenever I plug in an x value will actually tell me the slope of my original function f at that point. So let's just rewrite our function, make sure that we have it here. F prime of x is 3x squared. And this makes part B a lot easier because you can imagine it would be a pain to actually find the instantaneous rate of change at both of these values. You'd have to go through this whole limit thing twice for when x is equal to 0 and when x is equal to 3.5. Now we can just plug in 0 and 3.5. So first I want to find f prime of 0. Going back to my function, that's just 3 times 0 squared, and of course that is 0. I can also find the slope of the curve at 3.5. Remember, this is the slope of f, which is x cubed, 3 times 3.5 squared, and this will give me 36.75. Now, it's important to remember what it is that we found when we plug in an x value to f prime. So if you aren't confident in that, pause and think about it for a second. What we're finding is the slope of our original function f at this given point. So when x is 0, notice that the slope of my function f is also 0, meaning that it's perfectly flat. And if you graphed x cubed, and I'll just sketch a very rough graph of that. That's very rough. But notice at 0, if you graph it out on Wolfram Alpha, you'll see this. It's perfectly flat at 0. And that's why we get the slope is 0 when x is 0. At 3.5, we get that the slope is 36.75, which makes sense because it's positive, and we notice that my function x cubed is rising at 3.5, and so the slope should be a positive number. Okay? So I'm going to give you a couple more to try on your own that we'll talk about in class and will be presented by a couple of lucky students, and I will see you guys tomorrow. There are 2 more for you to try. The first one is based loosely off a problem from the book, so you can kind of look back at that problem to sort of check your answer, I guess, if you will. But I've changed it slightly to make it a little more useful in terms of what we've been looking at. And then number 3. Number 3 is a great question, and in fact, we've actually talked about this before. So it might ring a bell. For letter C here, this is a little tricky. So go through it and try it. I'm going to give you a hint in about 5 seconds or so. So pause first and then play again if you want a hint after you've tried it. All right, so for letter C, you want to know, will the slope of f ever be 0? Well, the slope of f is given by f prime of x. So what you're asking is, will f prime of x ever be equal to 0? In other words, can you find an x value that will make f prime of x equal to 0? So what you're actually doing is setting f prime of x equal to 0. So that's your hint. Go through and actually try solving that out, and we'll check tomorrow.